Hello, my name is Alison Collin and we're here to bring the work titled Simulation-Based Approaches for Autonomous Security and Monitoring Using Drones. In the recent years, we saw a rise in the application of drones, going from the military sector to the civilian market, and we see that the drones are a good tool for security and monitoring. Here I bring 4 examples of the application of drones on the field, doing tasks on security and monitoring. Despite being good tools for this sector, they still have some problems. The main problem is that they still need a human pilot, and this is occurs because of the lack of autonomy. To bring this, to increase this autonomy for the drones, we propose our work that utilizes a reinforcement learning method to navigate the drones through an environment doing tasks on security and monitoring. So introduce the method named distributional deep deterministic policy gradient, or DFRPG, for the navigation of this human area vehicle drone as a means to improve its training speed, its autonomy, and the capabilities of the vehicle, and the application of security and monitoring. So the DFRPG, it uses a distributed system of training, so it has multiple environments running in parallel as a means of speeding the training, and to better learn, it uses a distributional system for estimating the rewards that the system receives. So, as its basis, DFRPG has the method name Deep Deterministic Policy Gradient, or DDPG. This method uses an activated network where it has 2 neural networks, one to learn the policy and learn which action to take, that is the actor, and the other one, the critic, learns to estimate how well the system is doing, estimating their future reward. It has a deterministic policy, has an experience replay to store its memory. It has target networks to break the temporal difference, and uses soft updates to update traits, and uses noise on its exploration. So as a means to explore more of the environment instead of doing the quick action. So the DFRPG, as I said before, it uses DDPG as its basis, but it uses a distributional value function. So instead of learning to estimate a scalar value of a reward, it estimates a distribution for the rewards. In this work, we use a categorical distribution to estimate values with 51 bits. It uses an step return, so it estimates the rewards for n steps, and it has a periodic experience replay, so instead of sampling random experiences from the replay buffer, it uses priorities draw from the loss of the critic to better sample the experiences. And it has distributed training with multiple environments running in parallel. So here I bring the methodology employed in this work. First with the networks. The critic networks uses the state and the action as its input, has 3 fully connected layers with 256 neurons, and outputs a category distribution with 51 bits. The actor uses the state as inputs, has again three fully connected layers with 256 neurons and outputs the three velocities for the drone. The parallel training systems uses it's the distributed part where we use multiple parallel environments. Each environment has its agent, and this agent takes the actions and sends it to the environment. The environment sends back the experience that is composed of the state and the LR, and these experiences are sent to the replay buffer. From the replay buffer, the learner samples the experiences to do its training steps. After the training step, it sends back the priorities to the replay buffer so it can prioritize each experiencing. And the learner sends the actor weights to the agent, so the agent can choose which actions it's going to send to the environment. So here I bring how our simulation is set up. We use the gazebo simulator with rods. You can see a little bit of the environment with the obstacles, how the goal is set up. In the middle we have the drone. So for the drone we have three actions, the linear velocity, the angular velocity, and the altitude velocity. Our state is composed of the 20 LiDAR samples and from the distances to the goal, so three distances. Our rod function gives 200 when reaching the goal, gives minus 20 when colliding with the obstacles, and it gives zeros when the drone stays idle. So here we have our environment that is composed of a farm with a field of solar panels and a bar. The task for the drone is to navigate through this farm, reaching the goals that are random chosen. So here we have a bird's eye view of the farm. So we evaluate the method during its training. So we start evaluating at the first episode where it has 0 success rate. After 250 episodes, we have 40 to 50% success rate, and after 500 episodes, we have 98% success rate. So after the training, we evaluate the method, and here I bring a video showing how following the drone to its navigation to the farm. It goes to 4 targets and reaches success 3 of them. So in this work we introduced the property for allowing distributional version of DBPG to the task of navigating the drone on the security and monitor application. So the goal was navigating the drone to the obstacle field farm and we parallelize Gazebo and use Python and ROS tools to enable the different function learning methods. So we are used to enhance the autonomy of the drone for the public security applications. And as future plans, we include the application of this method on a real drone and developing a human drone interface so we can assign the objectives. So I like